some of the do's and don'ts with linear regression. First, we do not predict, x values with a given y value. What I mean by that is when you write an equation, you are only writing the equation directly from x to y. So if I flip back over here, this equation is used to plug in beer and get out blood alcohol content. You couldn't, for example, take someone's blood alcohol content, let's say they got 0.75, and plug it in here and try to solve backwards for beers. Mathematically, you could do that, but it doesn't logically make sense with the way the equation's written. We don't plug in for the hat the x variable. What you would have to do is you'd have to go in your calculator, you would have to switch and make a whole new equation where blood alcohol content is your x and beers is your y hat. It's perfectly fine to do, but the way the equation is written, it's only a one direct route from x to y. We want to avoid that thing that I just talked about on the back. Do not extrapolate. I forgot to put the rest of the word there. Sorry, extrapolate. Extra and polate, which means predicting far outside the x values used to create the regression line. You do want to always state what I call a disclaimer. Disclaimers are like things to kind of cover your butt and make sure you're not saying more than you actually know. That means that whenever you're doing your slope or your y-intercept, you want to say things like predicted, expected, estimated. Kind of pick whichever one is your favorite and use it every single time. Even just like approximately, that would work too, to indicate that it's a general trend and not exactly what happened from point to point. You always put a hat, y variable. I will take off for that. And you do not make predictions for nonlinear data. So the things we talked about last class about how mathematically I could type data in that's curved into my calculator and it'll do a line of best fit, but it wouldn't be appropriate to even use a line. That's not a good model for the data. So it's still important that we're looking at our scatter plot ahead of time and being like, yep, that's generally a nice straight arrangement, not bending or curving. We can apply a normal linear model. So now what we want to do is actually figure out what the calculator doing. When it goes in, it's like comes up with the line of best fit. How did it come up with that? This is not just me trying to teach you something that doesn't matter because, oh, my calculator can do it for me. There are times when instead of giving you the type into your calculator, they'll give you like a paragraph of summary numbers, and you're supposed to know how these numbers go together to make the line of best fit. So you really just need to know two facts. The first one is actually in your formula sheet explicitly, so if you still have that yellow paper, it's right here. It says that B, which we can see from our calculator or from our formula sheet, is the number next to x. Our slope is always r times sy over sx. So let's write that in our notes. B is always r times sy over sx. So this formula kind of makes sense. It's saying that correlation is not the same as slope, but it is related in terms of how you figure out the slope of the line of best. If r is positive, then your slope will be positive. If r is negative, then your slope will be negative. But the reason why it's not just equal to r is because r doesn't have any units. What we need to remember is slope is always change in y over change in x. So we take that correlation and we multiply it by literally the number that describes the change, and that's our standard deviation of the y's, and divide by the standard deviation of x to get it back into the units of the problem. So there's that point. The next, I think, kind of makes sense. It is that all line best fit always will go through the mean of the two data sets. So you have x data and y data, and so now we have two different means, x bar and y bar. That means the line of best fit will always go through that. Let me show you that with our beer and blood alcohol content. The average number of beers that were consumed was actually 4.8, so about here-ish, and the average blood alcohol content was a little over 0.07. If you go up to your line and over from 0.07, you should get right on the line of best fit. So you even did, when you drew your line, you were going through the average of the two data sets. I think that makes sense that you're trying to figure out a trend line, that it should go through the mean of the two data sets. And it ends up becoming like a toggle point, and then our line just kind of tilts left and right to make sure that it gives us the possible line. So if that's the case, then they help you out a little bit on the formula sheet, because they took your line of best fit over here, y hat equals a plus bx, and they changed it into y bar equals a plus x bar. What that means is you can plug in x bar and y bar for the line of best equation. You also can plug in your slope from down below and then solve this whole thing backwards for a. So try that out. But that's what you're going to use in your notes. The y-intercept can be determined by y bar equals a plus b times x bar. And then you're just going to solve for this a right here. That's your y-intercept. Alright, if you'd like to know a little bit more about why these two things are true for all lines of best fit, they go into a real detailed proof in your textbook. But I'm going to go ahead and show you how the line of best fit was calculated for the beers and blood alcohol content that we already did, and how I can get the exact same numbers that we got on the front. So what you get is this like paragraph with a bunch of numbers in it. We'll have to organize it. For our Ohio State blood alcohol content data, the mean number of beers consumed in the study was 4 point standard deviation of 2.2. So they're telling us about beers, the mean and standard deviation. And because beers was our x variable, our x bar is 4.8 beers, and our standard deviation for x is 2.2 beers. Then it says the average blood alcohol content in the study was 0.074, so that's our y bar, because BAC was our y variable, and with a standard deviation of 0.044. They also need to tell us our, because we need that for our slope equation, that from last class. Alright, so the first step is to get the slope. So we're going to use that slope equation we wrote down above, r times sy over sx. Be careful that you plug in the standard deviation for the y variable. Very common that our good students switch that up. So we're just going to type that in. I messed that up. I'm sorry. 0.894. See, silly things. Ah, that's right. 0.018. That's what we had on the front. You guys remember? 0.018 was the slope right here. All right. Then it says to calculate the y-intercept. Well, we have to do algebra for this. First, we're going to write down that y bar is equal to a plus b times x bar. That comes right from our formula sheet and from the concept that x bar is always a point on the line. So you're essentially plugging in x bar, y bar into y equals mx plus b, or plus bx, excuse me. And then we're going to put our slope in as well. So let's put in that our slope was 0.018. Our x bar is 4.8. Let's say plus a. And then our y bar on the left side is 0.074. Sorry, that a little bit backwards. So hopefully this algebra isn't too tricky for you. We're going to multiply times x bar, and then we're going to subtract that over to the other side. So I'm going to get 0.018 times 4, and then I have to do 0.074 minus that answer. Okay, that's a little different than what we had on the front. If you remember, it was negative 0.013, but that's close enough. We just had a rounding issue here, guys. So a equals negative 0.012. So if we wrote this equation with the variable names and the hat fun stuff, you get BAC hat equals negative 0.012 plus 0.13 times beers. All right, one more set of notes and we'll be done.